proceed and talk now about the curl of the electrostatic field. Again, I consider that everything we do today is, repetition of stuff that you have done in the past, perhaps with a different viewpoint, but exactly the same thing. So the first important thing we want to observe here, you're not interested in that. Observation is that the work done on a charge as you move it around the electrical field is independent of the path. Okay, so if I go from A to B, we've already used that, right? If I go from A to B like this, shortest road, or if I go like this, like when you're traveling with the NS, something, then it is the same amount of work, amazingly. It's not really in real life, but in electrostatics it is. Okay, and in particular, that means that if I was to start from a certain point and go on a path, go on a wander, and come back to the same point, then I would have done zero work. Okay? And that's a kind of very disappointing thing about life, because if we had done a certain amount of positive work here, then we say, hey, let's go the other way around, and this will be a negative amount of work. That means we can extract energy, and we just keep going around, and we get energy for free. Okay, so this is not the case here. The whole thing is equal to zero. So therefore, the line integral of the electrical field along a closed path P. The little circle in the integral here means closed path. The line integral of the electrical field around the closed path vanishes. This is equal to zero. Okay? And this is an absolutely fundamental equation. In the notes, it's called O-int, because that's the latex symbol for that, O integral. O-int of E is zero. Okay? And again, this fully deserves a wonderful box around it. Absolutely fundamental equation. Okay. I'm sorry? We are actually doing it for E because we're already working at the abstract level. We're not concerned with the value of your test charge. Yeah, so of course, when we compute the work, we compute the line integral of the force. However, with our test charge, we know what the test charge is. So what we're doing really is that we're computing the line integral of the electric field. Okay, and if I give you the line integral of the electric field, you can give me the line integral of any force on any test charge, provided you know the value of the test charge. Yeah, that's why we often do that. And you see, I do it too fast. Just go straight to the abstract level if you can. We're talking about electrical field. Nobody's seen an electrical field. None of you. Huh? But we're very happy. At least I hope. Okay. So that's one important thing. And now, very importantly, by Stokes's theorem, we can rewrite this as, yeah, so the integral around a path dl of the electrical field becomes the surface integral, okay, on a surface which is bounded by the path of BA dotting the curl of E. Okay, so here these are all like vector things, right? Okay, so here I'm just stating Stokes's theorem. Okay, so I have a path, and this is my path P. And around this path, you see, I can imagine a surface. I can imagine a drum-like membrane, but it can have any shape. The shape doesn't really matter, provided that the edge of the surface coincides with the loop defining my path. Okay. Again, I hope you're happy with this, right? So for example, if I use my absolutely stupendous drawing skills to draw for you a nice, yeah, I mean, it's wonderful, isn't it? So you see there's this kind of surface here that's bubbling up on that, like a cap or something. So this would be my surface S. Okay. And on my surface S, I would have these tiny little dA. So that thing here is a dA. Okay. The dA is a differential surface element. Right, so if I have just a plane, so if I imagine looking at a kind of big blown up version of that thing here, I've got my little surface like this. In that little region, it's got, say, a little dx, a little dy, okay? And there's a vector which is perpendicular to it that goes like this, okay? So d, let's say this is going in the z hat direction like this, just by choosing a local coordinate system. Then this dA would be dx, dy in the z hat direction, okay? That all rings a bell, I hope, right? Surface integral, differential element being a little cross section of the area, the tangent to the area. The numerical value of it is the actual area. The direction of it is just the normal perpendicular vector to the tangent. Okay, so you're all happy with this, right? And you're all happy also with Stokes's theorem. Stokes's theorem is, well, I mean, you should be very, very happy with Stokes's theorem, because Stokes's theorem is your friend. It helps you a lot. Whether you understand where it comes from is a different matter, but certainly you should be happy with it. But are you comfortable with the origins of Stokes's theorem? Yeah. So, and if not, please revise this, because this is really also the reason why there was this mathematical preliminaries and whatnot. If you need a reminder about indeed curls, divergences, and things like that, we just looked at it, sections 2.18, 2.14 in that book. Absolutely wonderful revisiting, re-explanation of all these operators and things, and then including the very important identities like Stokes's theorem, like Gauss's theorem that we'll just discuss later. Okay, so we'll make plenty of use of that. Okay, so now that's the statement here. So now by Stokes's theorem, we have that the integral over the surface conscribed by the path E of the curl of E is equal to 0. Okay, because that's what we have, right? So we just applied Stokes's theorem to this identity here. So I'm rewriting exactly the same equation in terms of value on the left-hand side. Okay, however, since this holds for any path, you know the symbol for any mathematics symbol, no? Okay, A upside down, A kind of tumbling down is like for any. Yeah. Yeah, everybody's comfortable with it? Actually, with my daughter the other day, I was like teaching her like some catch-up mathematics, and we needed a symbol for you know, not any, yeah, the contrary to this, and you know, you have the existence. Sorry, tangent. Yeah, existence doesn't exist, but actually this symbol doesn't exist. Yeah, so I wanted to name this after my daughter Marielle. There you go. So you use the Marielle symbol from now. Okay, back to the core content here. Since this holds for any path, and therefore for, you know, changing the surface here, we can glorify this equation from an integral equation to just kind of a direct equation, which tells us that the curl of E itself has to be equal to 0. Okay? Does everybody see this crucial reasoning? Yeah? Yes, question. So what I mean here is that the field I'll give myself a bit of space so you see it better. So this here, it's really for E at R at any R. Okay, so I don't write the argument, therefore I mean anywhere. That's the notation. So locally, the curl of your electrostatic field is 0. And here, just a word of warning. Only in electrostatics. Okay, so later on we will see that things get more jazzy when we put dynamics in there. For the moment, the curl of E is 0. Okay, once again, so just understand the reasoning, right? This is a reasoning which is extremely powerful because this integral relationship, you see, if I give you this for a given path, if I say for paths obeying this condition, then the line integral of the field is 0. Then you can't change the path because I've given you a condition which might prevent you from moving your path. But now I'm telling you, for any goddamn path you're interested in, whatever, I don't care, use whatever, you go woo, 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 okay? And the only way it can be true for absolutely every choice of path is if each time you move your path a little bit, you add 0. And the only way you add 0, you see, do you see where the curl comes from? Because if I take a path, let's say I have a certain path, and now I change the path. So what do? Well, I've got a line integral going like this. Okay, this is my path P, and it kind of carries on in the distance. You don't see the bit. This is just a kind of little section. I change the path. I go a little path like this now instead. So what do I need to do to go from one result to the other? I need to do an integral which follows then this line. I need to go zoop and then back here. Yeah, if you see what I mean. I would need to go like this and like this. Okay? That's where the curl comes from. So if the curl is 0 everywhere, then it doesn't matter because you're doing integrals like this of your vector field with the the curl of the factually this line integral like this corresponds to the integral of the curl of your field in that little area, which is 0. Okay, so that's how you can visualize that that thing. I don't know if that helps, but that's where it kind of comes from. Okay, I'm not sure this drawing is going to make like the editor's cut, but it's just a kind of illustration to show you where the things related to the curve. Okay, so that's one